Hey, good morning. Let's get started. Are there any questions for me? Yeah. Which one? For the assignment file? Yeah. My apologies. This was, I set up the link over the weekend, and then I was working on the notes, but I forgot to link it up. So just last night, I linked it up, late night, around 11 o'clock or so. So if anybody tried after 11 o'clock, you might get the notes. But most of the lecture today, I'm going to demonstrate HYSYS. Okay, so there's not really written notes for that. Once we complete that, that'll be the end of chapter 3. Then we'll move on to chapter 4. So I have put some notes for chapter 4 in that section, but we may or may not get there today. Okay.
You said you had something for the homework for assignment number 5, right?
Right, that's what I wanted to point out here. Instead of, pardon me?
Is that PDF or?
No, yeah, for assignment number 5, I posted the solutions, and it is with the TA for marking. Previously, I've just put the PDF file, which you will also find here. But in addition, on tutorial on MATLAB, I decided to kind of record as I develop the solution. So with all the mistakes, like how do I understand the problem and how do I translate it into MATLAB. So that thought process I've tried to record in two problems, problem 1 and problem 2. I will try to do that, and in the process introduce various features of MATLAB, continue to build on the MATLAB skills. If you have any other suggestion or topics that you want me to cover in tutorials, these are online tutorials. We're not meeting, but I'm going to just record and post online. Okay, so feel free to send me an email, and I will develop something for that. And if you go to mathworks.com, the developers of MATLAB, you will find that they have lots and lots of webcast lectures. The same idea. So they have a live webcast, and then they record that and they post it online for people to listen to it at their own time. So if you want to really become an expert in MATLAB, there are plenty of tools online. But what I will do is record things that are relevant to this course on solving various problems. Okay, so for every assignment, starting with 5, in fact, I will try to go back and see whether I can do that for 4, 3 as well. But from now on, you will see a solution as a PDF file, which will just contain the program and the output file. Basically what I'm asking you to do, and that is what the TA will use to grade. But in addition, you will also have an audio for every problem. And the audio is basically going to look at the problem, try to understand the problem, and how do we convert that into MATLAB. Now, for most of you who have done that already, you may just quickly go through it to see whether there are any new features in MATLAB that I've introduced, and those who have kind of struggled and there are aspects that you didn't understand, then you can find it useful. Now, if you don't find it useful, I will know, because there are no visits to that particular page. I know that you are not finding it useful, but give me other suggestions on how we might continue to build that part. But as you do more problems in MATLAB, it will become more and more familiar to you. The other thing I want to talk about is not a very pleasant thing, but I think I need to kind of reinforce. I do ask you, each one of you, to sign a pledge that you have not given help, etc. And I think you should, when you're signing it, you should take that seriously. This is not a fair comment on the whole class, because majority of you are doing well, but there are increasingly number of cases where I have noticed that people are copying and exchanging via email and things like that. I do encourage you to talk to each other. Okay, the process of, and if the only email program that you can transfer is to me. Okay, so if it is not working, I say go and send it, put it on TigerByte, or bring it to me so that I work with you in the office to show how to fix it. Okay, because I want a learning component there. If you just take somebody else's and then submit it as your own, that is the definition of plagiarism. Okay. Again, it's not meant for, this comment is not meant for the entire class, but there are increasing number of cases in recent weeks. So I just want to make sure that you take that pledge seriously and talk to other people. You can in fact show the program and say, help me find this bug, and all come to me. Okay, I'm willing to help. But just don't take somebody else's program and pass it as your own. That's not an ethical thing to do, because one of the things that you have to learn, not only how to solve, but also how to deal ethically and professionally. Okay. So with that comment, any comments that you have, anything that you want to bring up? No? Okay. We have been spending quite a bit of time solving nonlinear algebraic equations. Okay, that is the bread and butter of. Do you have a question? Or?
What chapter?
This, we are still in the last part of chapter 3. This is actually not in. What I'm going to do today is not in the book because it is HYSYS. Okay, but what I want you to appreciate is the link between what we have done so far and how it is implemented in HYSYS. And if you have already has anybody been exposed to HYSYS before? Has anybody used HYSYS? Okay, so this will be your first introduction, and you will probably end up using it quite a lot. If you become a chemical process engineer in any chemical plant, HYSYS or Aspen, these are the two process simulators. And they use all the techniques that we have seen so far. Okay, the algorithms, the building of the mathematical model, the degrees of freedom analysis, everything has been implemented. So after you use that, you might say, why do I need to learn all these things if everything has been made so easy for me? And we need to learn that there are limitations to such programs, and if they don't work, we need to be able to diagnose the problem. Non-convergence is a very classic example of that. Okay, so what I'm going to do today is take the same example that we have seen before, where we built the mathematical model. This is a single flash drum, and what you have is a feed with a multi-component feed with a certain composition, temperature, and pressure, and we flash it. The flashing process simply means I'm going to control the temperature and pressure in here in such a way that I produce two phases, a liquid phase and a vapor phase. And then gravity simply separates. The liquid goes down and the vapor goes up because of the density difference. Of course, this flash won't work in space shuttle, but on Earth it will work because gravity helps separate that. And what we are interested in is predicting what is the vapor fraction, what fraction of the feed goes to the vapor, and what are its composition. So all the outputs are unknowns. So we set up the mass balance, and we eliminated all the intermediate variables and obtained a single equation that can answer that question. What is the vapor fraction? And once I know the vapor fraction, I can calculate the compositions in the liquid and in the vapor in a sequential manner. Because the problem is so easy that we are able to separate the unknowns and the knowns and get an equation in terms of a single unknown psi. And psi is the vapor fraction. Okay? So if you give me what is the temperature and pressure in that vessel, then the first thing I would do is get all the K values. The K values are functions of temperature and pressure. Then you need to tell me what is the feed composition. And once I know the feed composition and the K values, the only unknown in that equation, which is a nonlinear equation. Okay? Why do I call it a nonlinear equation? Psi is the unknown. Do I have psi squared? Do I have sine psi, exponential of psi? It appears in the denominator and it appears as summation of several terms. And in each term it appears in the denominator. So when you take the product, if you want to take the common factor, etc., you will get a polynomial in psi. Okay? So it is a nonlinear equation. And you can solve that by Newton method, by secant method. These are the methods that we have seen. And once you get the value of psi, you can plug that in here and calculate the exit liquid composition. And once you have the exit liquid composition, you can plug that in here and get the exit vapor composition. So these are the things that we will compute. Okay. So we need to input K, we need to input Z. In order to do that, we need to know T and P. Now the beauty with a software like HYSYS is I don't need to know how in principle, I don't need to know how the mathematics is assembled, how the degree of freedom analysis is done, how it solves the equation. I just pull some few icons, connect them up, and define the problem, meaning you need to still input this, and it solves it as if by magic. Okay, but it does the same thing that we have seen. It goes and sets up the equations, solves those equations very dynamically. Okay, so that's what I'm going to show you. Another thing, we are treating T and P as parameters, as given numbers. Because if you can look at that equation on the right hand side has Z, which is the feed composition which is known. It has psi, and it also implicitly depends on T and P. What do I mean by implicit? If I change T and P, it's going to change K values, and the K value changes, it changes the performance of the vessel. Okay, so it's not directly appearing. T and P do not directly appear anywhere, but it appears in an implicit through another model, through another equation. And you can calculate that and plug it in here. Now, you can then ask the following question. Okay, instead of keeping T and P as knowns, as inputs, and psi as the unknown, can I do the inverse? That is, I tell you that I want 50% of the fraction in the vapor, and I tell you the pressure is 1 atmosphere. What should be the temperature? Okay, that is what you're going to do in your current assignment. These variations, okay, and all these variations can be done in HYSYS also in a very simple, transparent way. So it is possible. All you need to recognize is I have one equation that has 3 symbols appearing in it, so I have 2 degrees of freedom. If I can specify any 2 of them, I can solve for the third. Okay. Have you done thermodynamics yet? No. Okay. So I'm going to introduce a few more notions, and hopefully these will be reinforced later on. One is called a bubble point condition. The other one is called a dew point condition. What do you think it would mean? Intuitively, what would a dew point, let's say dew point temperature or dew point pressure. These are properties. The first point at which from the vapor, the first dew drops into a liquid phase. So if I know the temperature and pressure such that it's mostly vapor, but it's at the boundary where if I reduce the temperature or increase the pressure slightly, it's going to condense into the liquid phase. So it's going to rain out. All the liquids, the heavier ones in the vapor will drop off. So that will be called a dew point. The same thing in a bubble point. So if I have this entire mixture in a liquid phase, and I'm adding heat to it continuously, the temperature or the pressure at which the first vapor bubble will come will be called the bubble point condition. Okay, so we can calculate all these from this simple equation because they're all limiting cases of the general case that we have developed, where we have any amount of vapor and liquid. Okay, let's start building the HYSYS. If you go to the ChemEng lab, HYSYS is installed in all of those machines, and all you have to do is go and look for where it is installed. So you will see an icon like Aspen HYSYS. You just select that, and if it doesn't work, you need to go and see Rob Willis. The reason it won't work is often licenses. Okay, so it has to check a network license, and then it should give you a window like this. Okay, I'll just increase the size, and the very first thing that you will do is create a new case. Okay, and when you're creating a new case, everything is organized for you in a very nice fashion, the folders that you see here. So you have to basically go through these folders and define the problem. Okay, so the first thing that it says is components. So what are the components in your process flow sheet? You need to identify those components. Okay, so I'm going to say, okay, I'm going to add, and the component database is huge. There are probably about 2,000, 3,000 chemical components in there. Okay, so you don't have to worry about looking at their properties. Everything is put in database. Their boiling point, their critical temperature, critical pressure, and things like that. So I'm going to add these following components: ethane, propane. And how do I do that? I keep the control pressed so that I can select multiple items. Okay, these are the things I cannot capture. Okay, so I'll select, what do I have? 2, 4, 6, 7 components. Okay, so I'm saying that in my entire flow sheet, these are the 7 components that are going to appear. But as I said, the database is huge, and you can search search by the name, search by the formula, you can put filters, you can match, things like that, if you're looking for a particular component in your system that you want to simulate. Okay? So here I'm just taking a pure hydrocarbon system, and once you have selected, you close the window, and the next thing that you have to do is fluid packages. This one says what kind of property package you want to use to predict any property, whether you want to predict Cp, the heat capacity, you want to predict K values, which is our case in this case. Okay, we want to predict all the equilibrium ratios. Okay, and it gives you a default one by default, some property package. But for hydrocarbons, it turns out that there is something called the Peng-Robinson equation of state, which is the best one. So you can see there are a whole range of property package predictions for different kinds of systems. This expertise is what you will develop as you go through various courses, particularly in thermodynamics. You will see the theory behind a lot of these packages. Okay, the package is basically a set of formula that allows you to predict certain properties. So I'm going to pick the Peng-Robinson equation of state because I know that it is good for hydrocarbon systems. Okay. And then you can set up a lot of these parameters. You will learn as you need. Right now, all we need to do is I'm going to use all the default settings. I have those 7 components, and I have the Peng-Robinson equation of state. Okay, so I've selected that. I close this. So it changes to current fluid property package to Peng-Robinson. Okay, then I enter the simulation environment. So I've identified my components. I've identified my property package. Okay, so I enter the simulation environment. Okay, so I get this window, and I get another window here, and this is where the power of HYSYS Aspen simulators exist. Okay, so if you take the cursor close to each one of these icons, you will see it's a separator. Okay, here you have a 3-phase separator. If you have water, oil, and gas, for example, you have a storage tank, you have a cooler, heater, heat exchanger. You will see the theory behind each one of these, the models behind each one of these in the courses that you are going to see in the future. Okay, and there are some powerful tools for distillation columns. Okay, we can simulate the entire column of 50 trays or whatever and predict what is going to be its output compositions and flow rates. The model behind that are really very sophisticated. Okay, but they are all algebraic equations, nonlinear algebraic equations, because this is a steady state process simulator. Now, there is a dynamic component that we will see later on, but we're going to see the steady state. So what it means is if the plant, chemical plant, is operating under steady condition, that I have constant feed, crude coming into the refinery, and I have constant products that are going out, gasoline, aviation fuel, diesel fuel, whatever. The whole thing is operating under steady state, then I should be able to predict, if I put certain amount in, what are the various compositions. The next question would be, can I change the operating conditions so that I can change, suppose the demand for gasoline is high, I want to produce more gasoline, can I change the condition so that I can take a gasoline cut that is produced in a larger amount. So those are the questions that you can play with, what if scenarios. But how do I build a process flow sheet? Okay, so let me expand this. And I'm going to do just a separation vessel, a single and a 2-stage separation vessel. Okay, so I go to the separator, click on that, and you see it becomes selected, and I just drop it here. Okay, so that is a separator. And then I need, the separator has inputs and outputs. The inputs could be material streams, or the input could be heat. You are heating it up. So there are 2 streams that you will see here. The blue one is the material stream, and the red one is the energy stream. Okay, so you'll have inputs and output streams that you need to connect. So in this particular case, I'm going to have 3 input streams. Okay, so I select one and drop it there. I select the second one and drop it there, and it automatically labels these for me. Stream 1, stream 2, stream 3, and the process equipment itself is V100. Okay, and then I have assembled the streams and the equipment. This process you can repeat and add more. Okay, if there are any questions, please do stop and ask me. The next thing is I need to connect them, attach mode. So I go to this attach mode, and that button gets pressed there, and then the icon changes. So as I take the cursor around, certain things light up. Those are the inputs and outputs. So if I go to the green, for example, says feed stream. So you can connect a feed stream to that process. This material stream itself will have an in and an out. Okay, so here if you take the green out and then press the mouse button and drag it to connect. So it connects that input to that particular feed. And then here you have, take the cursor close, it says it's a vapor product. Okay, so I can click on that, but keep it pressed and then drag it. This takes certain time for you to get used to it. Okay, keep it pressed, keep the mouse button pressed, and then drag it along. And this is, it says it's a liquid, should say it's a liquid product. I guess it's not fast enough. Yeah, there it is. And I press that, and then I connect it. That is the simplest process flow sheet. We have assembled our simple process flow sheet. Okay, and this is going to solve the equations that we have seen here. This is the equation it's going to solve. Okay, it's a flash drum, and so the specifications and stuff like that are drawn from this model that we have built. Okay, what do I do next? What do you think intuitively? What do you think you would do next? You have assembled the process flow sheet, right? You have identified the input and the output. It's all just graphical. Underneath, there are equations that are being assembled for you, right? And it's going to be able to predict. So if you click on the stream, double click on the stream, any stream, it opens up this window, okay? And here you have a worksheet, an attachment, and dynamic modeling. But we'll just look at the worksheet. So the conditions, the properties, the compositions, the K values, all your job is to fill out these forms. It will give you tables after tables at the input side. You fill these out. For that, we need to understand what is the model, what are the possible inputs that I can give to that particular process unit. Okay? So in the case of a flash drum, I can go in here. It tells me already I'm dealing with stream 1. I press this, for example, and enter 0.5. So I'm asking this process to produce, that stream should have 50% as vapor. Okay? And then I'm going to specify anything that is in blue, you can specify. Okay? And I'm going to specify the pressure. So I click on the pressure and specify 1. And then it tells me what are the units. What is the unit of that 1? Now, it didn't ask me for vapor fraction because it's a dimensionless number. But pressure is a dimensional number, and you can select the units to be anything you want. Okay, so I'm going to say it is 1 atmosphere, for example. Then it automatically converts to 14.7 psia because it displays in that unit. But you can customize these too. Display units can be customized through preferences. Okay, and you will see in here, the yellow line here says unknown compositions. So this is where it is enforcing the degree of freedom that we have seen in analyzing the problem. Okay. Once the degree of freedom is completely specified, that is everything that it needs, if you have specified that, that will turn into green and it will automatically solve the problem under those conditions. Right now, it's not specified yet. Do you have a question?
Yeah, if you have multiple reactors connected to each other, does take into account the distance or the orientation to each other? Affect the calculations at all?
Why would you think the orientation would affect it?
Well, if you had bins in the pipe, wouldn't that affect?
It will affect something. What would that be?
Well, you could have expansion bins. Or you could
if you have a certain length between two process units, and you can simulate that. So if you're transferring the fluid from one unit to the other one, you could lose heat to the surroundings. So the temperature that comes out at the end could be different from what you're putting in the pipe. The pressure will also certainly be different. Okay, so there are pipeline segments. So if you want to track that, go in here, gas pipe, or is it a pipe segment? So you put that as a model, then only it will do the calculation. But if I just take a stream and connect it to another stream, it doesn't have any information. So it says whatever comes out of this stream goes into the other stream. Okay, good question. Okay. Okay. So it hasn't finished the problem specification, but it gives us the hint, unknown compositions. Okay, let's go and put in the composition. It shows me all the 7 components that I have. Okay, so I go in there and enter 1. And then in the first one, I entered 1. Immediately it says, okay, input composition stream. And it makes it a little bit easier for me to enter those. If you have a composition from a GC analysis in a plant, you will enter all those. But this is only a demonstration. So I'm going to make my job easier and say equalize all the compositions. So it enters the same composition for all of them. So it is an equimolar mixture. Each one is appearing in the same amount. Now, it says mole fraction, but mole fraction must add to 1. It cannot add to 7, right? So it has another feature called normalize. Okay? So it normalizes that, and then I have a mole fraction of 0.1429. Now, you can go and change this to 0 if you want, okay? And then say normalize again. Okay? So, let me just keep it as equimolar mixture. And press OK, and that's it. So, I've entered all the compositions, okay? Then it says, oh, unknown flow rate. Okay? We haven't specified how. Remember, in the feed, we said we have to specify, where was that? The feed rate, the temperature, the pressure, the compositions. Instead of temperature and pressure, we have chosen to specify pressure and vapor fraction. But you can specify the temperature if you know. Okay? But I don't know what the temperature is. That will make it as a two-phase mixture. So I said, okay, take the vapor fraction as a given and solve for the temperature. Okay, so let's go back to the condition and look at molar flow rate. And let me say I'm having 100 kmol per hour. That is my basis. So I'm assuming that I have 100 kmols per hour entering. And I enter that. Immediately it turns green. It says OK. So everything. So what it has done is enforce the degree of freedom analysis for that particular stream. These are the variables that you need to specify, the minimum number of variables, and if you specify, I calculate everything else for you about the state of that particular stream. Okay? So in fact, it calculated the temperature to be 90. Now it changes from blue to black. You cannot change it anymore. Okay? So if you want 50% of that feed stream to be in vapor state, at a pressure of 14.7, at a molar flow rate of 100, then your temperature of the feed stream must be 94.58. in degrees Fahrenheit, or if you take it near that, it also shows you in degrees C. Any questions so far? Am I going fast? Are you guys following me? Yeah? Any questions? Now, I have a question for you. For this particular stream, I want to know its bubble point temperature. How can I get it?
After you look up the species, so the vapor fraction is 0.
Set the vapor fraction to 0 because it's a mixture. It's a mixture of 7 components, and that mixture contains equal amounts of all those 7 components. So if I take that mixture, ethane, for example, is the first component, most volatile, so it will start bubbling first. And octane is going to be the last one to be driven off. Each one has its own boiling point. Okay? But when I have it as a mixture, I'm asking the question, at what temperature will this mixture begin to boil? That is my bubble point. So that at that condition, my vapor fraction is almost 0 because I'm just producing the first vapor bubble. Okay? So the vapor fraction of the feed is 0. So if I go there and set it as 0, I should get the bubble point. Will it be more or less than this? 94.58 that you see. Minus 53.93. Okay. So if the temperature exceeds that limit, then you will have the very first bubble. So dew point. If I want to get the dew point, all I have to do is put 1, and that should of course be much higher. So this mixture is going to have a range of temperatures in which what is the beautiful information that we get out of this? We know if the temperature of the feed is somewhere between minus 53 degrees and 176 degrees, you are in a two-phase regime. You are going to produce some amount of vapor, some amount of liquid. The composition will be different. Yeah.
Did it fill like the value stream?
Very good question. So how did it get the K value? Can we get access to the K values? Okay. And will the K values change as I change the temperature and the pressure? Obviously, it will change. Okay. And it makes a call to the Pring-Robinson package and says, this is my feed, these are my temperatures and pressures, you calculate the K values and send it to me. Then I can solve this particular problem. How do I get the K value? There is a table there. So those are the K values at that particular condition of temperature and pressure. There is a lot of calculation involved behind this. Okay? And you will see in a thermodynamic course, how is the K value calculated? In physical chemistry, have you done that? I'm trying to relate to what you have done so that you have some idea. Well, this course is probably too early but you will hopefully this course will resonate with the rest of your stay in LSU. When you hear these things in other courses, you say, yeah, Kumar mentioned that, but I forgot. What you need when you have a vapor and liquid system that are in equilibrium, you have something called a chemical potential or a fugacity that is the same in both phases. It is that principle that is used to get the decay values, and HYSYS does it for you automatically. And you will see these values change as you change the vapor fraction or the temperature or the pressure of the stream. Okay, any other questions? Let me put it back at 0.5. Okay, so what I have done so far is I have specified only the streams, okay, the inlet stream. So let's now, that is the inlet stream that is coming into this vessel, and I need to see what happens in the vessel. Okay, so here I have an optional energy stream, meaning I can add heat to that vessel or remove heat from that vessel to adjust the temperature and pressure condition. But if I don't do any of those, okay, it is an adiabatic flash column, meaning there is no heat exchange between the vessel and any of the surroundings. What do you think should happen? I just bring the feed that I have defined, which has, under those conditions, 50% of it is vapor. Comes into it, and they just dump it into this vessel. Okay, it's a mixture of 7 components, equimolar, at the pressure of 1 atmosphere with 50% vapor fraction, which happens to be at a temperature of, whatever the temperature was, 94 degrees. Okay, I take that feed and dump it in here. What do you think would happen? Half of them will go to the top, half of them will go to the bottom. Okay, and does it say that to us? Let's click on it. Does it make sense? I want you to be able to learn to read this. Okay, so this is the properties and the conditions of the stream 2, which is the vapor stream. Okay, vapor stream. So what is the temperature of the vapor stream? It's the same as it came, because it is an adiabatic. It is operating under adiabatic condition. You are not adding or removing heat. Okay, so it is coming in at the same temperature and it's leaving at the same temperature. It's coming in at 14.7 pressure, it's leaving at 14.7, but it says the vapor fraction is 1. Does it make sense? It does, because we have separated it out, right? So all that comes to the top is in its vapor state under those conditions. But what should its flow rate be? Half of it. And there you see, mass flow rate. We put 100 kilogram mole per hour, we're getting 50 mole to the top, and we'll have 50 mole to the bottom. Okay? What should the K values be? Same as before, because the temperature hasn't changed. So if you compare this, I guess I'm wrong, is it? I don't remember what it was. Let's open that up too. I would expect it to be the same. I guess it is, yeah. I just remembered it wrong. Where is the other window? Stream 1, stream 2. So let's put them side by side. Okay, so I'm trying to compare what we fed and what comes out in the vapor stream. You can also open one for the liquid and compare it. So the K values are the same, the temperature is the same, but the flow rate is 50% of what we put in. Okay, what do you think with the compositions? The compositions we put in are all equimolar. Can anybody guess which would be higher in the vapor phase and which would be lower in terms of composition? Yeah? Ethane should be the highest because that's the most volatile one. Okay? And N-octane should be the lowest. So N-octane is 0.0097 mole fraction. Okay? Whereas we put in 0.1429. Okay? And ethane we put 1429, but we're getting 0.2782. Now you have a tool that you can change the temperature, change the pressure, change the vapor fraction, any of those 2 degrees of freedom, and look at what is the product that you are getting. Okay, this is what a typical process engineer would do most of the time. You'd be trying to optimize your performance by playing with the degrees of freedom that you have to meet a certain output target criterion that you have. Okay, any questions? Okay, and you can open up the liquid stream and compare that. Okay, the composition obviously should be the other way. Octane has more in it, in the liquid stream, and very little of ethane. Now, the problem is if I want to get rid of completely ethane, these are units that are commonly used, deethanizer, debutanizer, names that are given to the vessels, and the idea is that you should get rid of the composition to 0. What does this tell us? This tells us you cannot do that in one stage, and this is why you need multi-stage. Okay? In the multi-stage column, you can completely get rid of one component from the top product or the bottom product. Complete meaning 0.00001, almost trace amounts. Okay, so that's how easy it is to use HYSYS. How many of you think it is easy? You would agree. It is fairly easy. Okay, but what you need to have in order to use it without making any mistakes is a conceptual understanding of what the problem that you're solving, the models behind it, and the methods that are used.
So if we change a value of the parameters of the system, they automatically adjust the rest of them to fit.
Exactly.
How can we make it hold certain values at constant, as a constant defined instead of changing? So we'll change other variables.
That's more sophisticated. It's a good question. It is possible to do because that is the kind of tool that you need. Because you might say, I don't want to do a trial and error tracking 100 temperatures, but I know that I want the propane composition to be a certain value. So what you're doing effectively is saying, I want to transfer the degree of freedom to one of the outputs. I want to fix the propane composition to be 0.15. Find me the temperature and pressure that will do that. Okay, and that's not easy to do because the way that we have set up the equations, we're solving for the vapor fraction or solving for the temperature or the pressure, and then calculating the composition. Think of it how you would do in a MATLAB situation. This is what you're going to do in your current assignment. You will hopefully reinforce all these ideas because I'm asking you to do the same thing in MATLAB and then in HYSYS and compare the two results. Okay, what would you do? You know root finding, you know bisection. Okay, so you know how to guess and verify whether the guess is right or not. So you put a loop around the solver and say, I know only temperature, so I'm going to give you a guess of temperature, and you predict me the propane composition. I will compare it against that. And if it is not 0, the difference between what I predict and what I want, then I will predict the next value of temperature guess using bisection method, using secant method. Okay, so I can now iterate on that because computers are very good in this trial and error. I don't want to do it testing for 100 temperatures, but I can let the computer do it by putting a loop around it. That is how you would do it in a MATLAB. In HYSYS, they have the same features. So they would put a loop around it in an iterative way to answer questions like this. I want a certain composition in a certain stream. You can transfer the degree of freedom to that, but there is something called adjust. I have not prepared myself to go through that today, so I'm not going to do that now. But I'm just telling you that this adjust block, so you need to have a block that you put in, and I will go through this in a later lecture. Okay. So in the adjust block, you say this is the variable I want to meet a certain value. And this is the degree of freedom. So you go and adjust the temperature such that it meets the specified value for propane composition. So that adjust block will identify a target and a variable that it is free to change. And then it searches on the variable to meet the target. So that gives you a very powerful tool because you can now match almost anything that you want in the plan, as long as you transfer the degree of freedom. So the concept of a degree of freedom is very important to understand. You cannot achieve any propane composition at any condition. You can achieve only at certain conditions. You want to know what conditions those are, and those things can be answered from this. Okay. Any other questions? Okay, so suppose I put a second stage because I want to bring the composition of N-octane to a more richer value. From 0.27, I want to increase it to 0.35 or 0.4. How can I do that? Put another stage, a single stage. Column we will see later on. Okay, so now looking at, we know how to solve. So I'm trying to build on this particular problem. So what we have done so far is learned how to solve this. This is the equation that particular unit, the flash unit, solves. Okay, so what I want you, I'm preparing you now to do your current assignment, because these are the questions that I've asked you to do in the current assignment. Okay. So if I add a second stage here, for which this is the feed. The output from the first stage is the feed to the second stage, and I'm going to get two more outputs. How easy it is in HYSYS, we will see that, and I want you to implement the same thing in MATLAB. Okay, so what does that mean? You have one flash equation for the first stage, you must write another flash equation for the second stage, and solve in sequential manner. For the first stage, you can completely solve for it, because you know how to get psi by solving this, and you know how to get the x and y. Those are now then you know what the liquid rate is and the composition. That becomes the feed to the next stage. So you just cut and paste that part of the MATLAB code to solve a second stage, but redefine your feed condition to be the output condition from the first one. So it is not very difficult to extend this in MATLAB to solve two equations. But the thing that you need to realize is that it is a sequential process. They are not coupled. You can solve the first stage independently, take the output, feed it to the second stage, and solve that independently using the same mechanism that you have used for the first stage. And that is where HYSYS derives its power also, because all these units can be stuck on one on the other, and then the output from the one is the feed to the next one, and it knows the equations. It can solve that automatically for you. So if I want to do that, I just select the second stage and drop it there. But I need two more material streams. Okay, and I need to connect them. So I go to the output from here and make that as the input. Okay, and then I have an output from there and an output from there. Oops, getting not connected. Now, if I already have solved for this problem, composition of stage 3. I mean, in the compositions and conditions of stream 3. Okay, so that is the one that is coming into the second stage. Okay, so what do you think will be the temperature pressure composition of the stream 4? Why? Because this is coming in as a zero vapor fraction. It is a pure liquid stream. Okay, and it is coming in at a temperature of 94.58 and a pressure of 14.7. I'm not doing anything to it. So if I just take a liquid stream, which is happy to be in that state at that temperature and pressure and composition, I dump it into the next stage, I'm going to get the same thing out. Okay, so the molar flow rate in the liquid is 50. So all the 50 that I put in the feed comes out as a liquid at the bottom. If I open the top one, I'm going to get zero flow rate there. Molar flow rate is zero because nothing goes to the top. How can I evaporate some of this liquid? Yeah? I can add some energy to it. I'm heating directly. I have a heater in the vessel. I'm adding some energy to it. Now, this is probably a tougher question. How much energy should I add to achieve a certain separation? That is, I want 50 moles is coming. I want 25 moles to go to the top, 25 moles to go to the bottom. Pardon me? It depends on the composition, depends on the thermal properties, a lot of things. But those are all automatically calculated by the program. All you need to do is put in a certain number, how much of heat you are adding with a heater, steam heater, electric heater, whatever you have. So I have no idea at this stage what number I should put. How would you get a meaningful number? How would you guess at a meaningful number to evaporate sufficient amount of material? For example, if I just say I'm putting 100. Oh, not there. Oops. Here. 100. What does that 100 mean? Sorry, not even.
Say, is there a unit?
Yeah, this is just a stream. What it does is it adds an energy stream, because I forgot to add an energy stream. Okay, so it will add an energy stream and it will label it as 100. There it is. So I entered in the box I need an energy stream, and this is actually the label for the energy stream, not the duty. But it still says unknown duty. I don't know what is the duty here means how much of heat, physical heat in kilojoules per hour that I must add or remove. Okay. So all I've done by entering 100 is label that energy stream as 100. And I click on the, I could have also done this. I could have pulled this energy stream, added it there, and connected it visually if you want. Okay. So now I double click on that. Here is the place where you specify the heat duty, kilojoules per hour. So I just put 1000. Okay. Then it says, okay, if you're adding 1000 joules, I can now calculate what would be the vapor fraction. So I can go and see that I'm not really producing any appreciable. If from that table I say calculate the vapor fraction, how would you do that? You know the molar flow rate, 0.00778. So I'm producing very tiny amount of vapor, right? So the heat I've added is not enough. So that divided by what? Divided by 50. Because 50 is the kilomoles per hour that you're putting in. So if you want the vapor fraction, if you want to calculate the vapor fraction, take the molar flow rate and divide it. Okay. So obviously this is not sufficient. So what I need to do is keep that and try increasing, maybe to 20,000. Okay. Where is the other one that disappeared? Now I'm producing 0.16 out of 50. Still not sufficient. Now, one of the things that I want to see whether you can guess a better value for this number. Yeah.
You can't specify the molar flow rate in the 2, 4, and then it tells you how much heat to put in.
You can do that with adjust block. Okay. So that is where you are transferring. Right now, you give the input and it calculates the output. So if you want to specify something on the output stream, then you have to use this adjust, so-called adjust block. You say, this is the output I want to adjust, and this is the input I can change. So I can couple the vapor fraction or the vapor flow rate to 25 and say, make the degree of freedom of the heat duty. Then it will automatically solve it for you. I have not gone through this last night, so I don't want to try it live in front of you to how to use the adjust block. So let's, you are welcome to try these things. That one of the things that you should do is play with it and learn on your own, but I don't want to take the valuable class time to kind of figure it out for myself in front of you. Okay, but it's not very difficult to do. Or you guys want to do it? Let's do it one day. We'll take some more time, but let's take the question that we want to solve is, I want the molar flow rate to be 25, and you all have to be alert and guide me doing this because I'm flying blind now. Okay. So the goal is to get 25 moles per hour in the feed, in the vapor product by adjusting the heat duty. We need to figure out how to do that. Okay. So I'm going to take the adjust block and put it there, somewhere there. Oh. Okay, there is the adjust block. Okay. This is how you would learn for the first time a new thing. You just double click on that and see what does that block do. Okay. So here is the adjust name and the connections and adjusted variable, select a variable. So let's try that. Okay. So what do we want? We want, I guess I need to keep going back and forth. We want stream 4. So select the stream 4 and look at the amazing power that you have. For stream 4, you can specify, I think I told you guys last week. Last week we had a gift assessment, but today we have Casey from College of Engineering. She would want to talk to you, I think, at the end of this, maybe about 10 minutes before I will leave again. But this is just to get your feeling on how the use of technology is helping you or hindering you and things like that. Okay. So now you need to help me going through that list to find out where I can specify. I can specify the bubble point, I can specify the dew point, I can specify so many things. Good. Molar flow. Okay. And I want to specify the molar flow, but it's not giving me a value where I can put that. Let's say okay. So object for adjusted variable molar flow rate. So we identified which stream and what property we want to control. The next one is, sorry, I already made a mistake. It says adjusted variable, right? This is the variable that it can adjust. The target variable is what we want. So we want the target variable to be stream 4, and that's why we didn't get a value to be specified. So the target is molar mass flow. Where is molar? Molar flow. Okay.
You adjust the load on the target values.
User specified. Yeah, target value here. So we want the target. Thank you. That's very observant. Okay. Target value want to be 25 kilogram mole per hour, and the adjusted variable is wrong. What we specified. So what should that be? Should actually be stream 100 because that is the heat stream, and we want the heat flow. I think so. I don't know what heat flow 2 is. I told you I'm flying blind because we are exploring something new. Okay, and just say start. Let's see. Adjust is at the maximum iterations. This is where this course comes in help. What happened here? How do you interpret it? It tried maybe 20 times or 30 times. And it's at maximum variable after 10 iterations. It tried 10 attempts adjusting the heat duty to produce, and it gave up. Now is your challenge to come up with a right initial guess for that adjusted variable so that it will reach there in 10 iterations. Or what else can you do?
You specify
You find out where I can specify to increase the number of iterations. Okay? So you should understand these concepts of what are iterations, what is the maximum number of iterations, so that you have the path forward to jump across this hurdle that we have. We have specified the problem, we have seen, it's not really bad, we figured it out in 5 minutes, right? How to set up the adjust block. It's basically identifying the target variable, the adjusted variable, and specify the target value. What does it say? Oh, it says actually continue. Let's continue. Another 10. Oops. Okay. I hit no by accident. See, by default, it puts me on the no. It's not going to get there in the right number of, because you already know the initial guess that we had was very poor. If I had 20,000 kilojoules per hour, produces only 0.1 fraction or something like that. So we need to have a lot of heat. So let's get back to that track. How do I find out how much of heat should I approximate ballpark?
All the thermodynamic equation.
But it already does for you. That's a good point, but it already does it for you. So all you need to do is look at what is the heat content in that stream. Okay. So there is one place here where you can extract that information. Molar enthalpy. Okay. So it says it's about 207,000 kilojoules per kmol. That is the heat content in the stream that comes in. Okay. So from that, if I remove 20,000, it's not going to matter because it's only 0.1%. So I'm going to vaporize only 0.1%. So from that number, can you come up with a better guess? By simply looking at the number, it says the enthalpy of that stream is of the order of 2 times 10 to the 5.
50% of it?
Try 50%. Take out 100,000 of that and see what it does. Right? So let me get rid of the adjust block now. How do I get rid of that? Yeah, you need to also learn how to readjust your stuff. Right now I am in attach mode. I get out of the attach mode, then I get this hairline cursor. So if I go and select that, then I can use the delete to get rid of that completely. Okay? It deletes also the associated streams. And then I can go into that heat stream and change that into, oh, it is already getting there. This is the iteration that was happening. Remember, what was the last number we had there? About 20,000. But right now it has 8 times 10 to the 5. Okay? So it was, the adjust block was trying to get to that number, and in those 50 or 60 iterations, it has come there. Now, you may want to say, okay, at this stage, what is the vapor fraction? There. From about 0.1 kilogram per hour, kilomole per hour, it has gone to about 15. So if I had pressed that button a few more times, if I had the patience, I would have gotten to the answer, right? But we have another way of getting at that particular number, and that is trying to increase this to maybe 100,000. The moment I enter, it solves the whole problem. It immediately, instantaneously updates what the output is. I determined something is wrong. You guys all know it, I don't know it. A million? Okay, thank you. There. Almost like, now you won't do 2 million because you have gotten from 0 to 19. If you put 2 million, it's going to be 38. Okay? So now you use the bisection idea. Okay, so it's going to hit the target. Okay? Pardon me?
What happened to the adjust?
I deleted it. I was just impatient because I should have figured out how to increase the number of iterations and let it do, or it gives you 10 iterations at a time. But when I quit, it was already approaching that limit because it was already evaporating about 18 or something like that.
So it stopped where you stopped, like you were clicking yes.
I stopped. It automatically puts it on no. That's why I accidentally hit no and it stopped.
When you were clicking yes, you said that it would be more like 300.
Oh yeah, it would have exactly found 25. It would have found out exactly what is. When I say exactly, there is a tolerance. There is an error. Okay. Within that, there is a default value for that error. Within that error, it would have found out what is the heat duty to produce 25 moles per hour. Yeah. Okay. So these are powerful tools. HYSYS is a powerful tool. MATLAB is a very powerful tool, and you will continue to learn, hopefully, as you're going through the other courses. Any questions? The current assignment, I'm asking you to do exactly the same thing, but on the vapor side. Build one, build two, but I'm also asking you to solve the same thing in MATLAB, because I want you to develop the appreciation. What HYSYS does is nothing more than what you can do in MATLAB. Of course, these are all written in C, but basically assembling the equations, solving the equations using iterative methods. Any questions? Okay, for this lecture, that's all I wanted to do about HYSYS, and that completes chapter 3, okay, on nonlinear algebraic equations. We still have some time, so let me just set up the problem for the next topic, which is, let me tell you what the problem is about. This is called functional approximations, chapter 4, okay. What is functional approximation? We have already seen parts of it, but we want to build on that. And why do we need it? Why do we need functional approximation? So for steady-state models, we have seen we get a system of algebraic equations, nonlinear algebraic equations in the worst case. And we have seen tools for solving them. But the moment you go away from lumped steady-state model, you get differential equations. You get either ordinary differential equations of the initial value type or the boundary value type. So now you are constructing functions. Okay, solutions are no longer just numbers, but they are functions of either x in space or time. Okay, so we cannot get solutions to these problems analytically because their problems are nonlinear. But we have seen tools in MATLAB. We have seen ODE45, we have seen BVP4C. You have used both of them in your previous assignments. Now we want to open that up and see how does ODE45 do it? How does BVP4C solve such problems? So we're going to look at the theoretical part, the algorithmic part of how do we approximate functions and how do we improve those approximations so that we get the solutions. The ideas are very similar for solving system of algebraic equations because there we had an approximate guess and we found out a way of improving that guess in an iterative manner. And we saw ideas of convergence and the rate of convergence, etc. So there are two types of problems that we will need functional approximation. The first one is, given a function f of x, I know what is the function f of x is, but it is a complicated, messy function. Okay? So I want to be able to evaluate it, so I want to represent it by a simpler function, a polynomial, for example. So again, I asked you to think about this before. EXP, exponential function. If I want exponential function of 2, how do I evaluate that? How does your calculator do that? You just enter number 2 and then you press the button EXP, your calculator spits out a number. In MATLAB, you just say EXP2, it spits out a number. So in one of the tutorials, we saw how MATLAB does it. There is a series expansion for it, and it takes enough terms in this, and it's an infinite series. So we don't want to add up all the infinite terms. We take enough terms in that, and we truncate it. We leave the other higher order terms, because they are adding lower and lower amount in terms of magnitude. So we can get any desired precision by simply taking enough terms in that series. Okay? So for such functional approximations, we will need to develop a mechanism by which we construct an approximation. The second one is more, I guess there should be an I there, more useful for chemical engineers or most engineers, I would say, the situation where you have a set of data, just observations. Okay? You have a reactor, you are monitoring the concentration as a function of time. Or you have a reactor, something called a plug flow reactor, you are monitoring the composition as a function of position in the plug flow reactor. So you get two sets of data, the dependent variable y and the independent variable x. And you want to plot them as a function of y against x in the form of just data. The data might do something like this. Okay? So you want to represent that by an equation, by a function. So once again, you need a functional approximation. You want to put a curve through this that meets, for example, as accurately as possible the existing data, but also gives you the power to predict what will be the value in between. If I have that function y as a function of x, then I can put any value of x and get the value of y. So this idea is called the interpolation. So if you want to predict values at other points, other than the data set that you have, you're going to develop interpolation algorithms for doing that. Okay? So these are the two reasons why we would want to have functional approximations of either a set of data or a given function or an unknown function, which is excuse me, unknown function which is a solution to a differential equation. So this will develop over the next several lectures. Any questions on the basic framework, what we are trying to do in chapter 4? Okay. Casey, how long do you need?
10 minutes.
10 minutes? Okay. I'll talk five more minutes and then I will hand over to her. Okay. I'm not sure whether you have heard of this function called ERF. Have you come across in any math course? What is it called? Error function, as the name says there. But it is expressed in the form of an integral. What is error function? It is simply e to the power minus psi squared d psi integral. So if you want to represent that graphically, what you need to do is, question? You need to plot against psi this function e to the power minus psi squared. That means you can take different values of psi and plug it in there and you'll get a curve like this. But error function is not that curve. The error function is the integral, that is the area under that curve up to a certain point x. But the x itself is a variable. So x could be here or x could be somewhere here. Okay? Then I will have to take the area under that curve up to that particular point. So the error function has the unknown variable as a limit. Okay, the upper limit is the unknown variable, and you put that certain value and you need to evaluate this integral. Now, does MATLAB know about it? How can we evaluate the integral? Let's just go and open up MATLAB. This would be the theoretical part, so it may put you to sleep. Some of you at least, I hope, you can keep the interest. I think HYSYS is easy because you can see it and you can understand. Okay? But when you have to deal with equations, you need to pay extra attention. It's taking a long time. So what I'm trying to show is, is there an analytical expression for that integral? Okay, the answer turns out to be no. We cannot integrate that analytically. So what mathematicians do is, whenever they come across such complicated expressions, they just give it a new name. Okay, exp is one name that we give to a particular infinite series. Sine, cosine, they are all infinite series. In the same sense, error function is an infinite series, and we will see how that series can be constructed. But MATLAB has an understanding of that error function. So E or F 0.5. So it does know about the error function. It can give you the value for any value of error function. What would be error function of 0? You can say, okay, it starts with 0. And what would be the error function of 10? It's 1. Okay, so can you plot that error function to get a look at a shape? How would you do that? You create x equals 0.110, and then y is equal to error function of x, and then plot x comma y. That's how the error function looks. Okay, so it's a function that starts from 0 and then goes towards 1. It's well scaled, and it is almost 1 above a value of 3 or 4. Okay, and it asymptotically reaches a value of 1. Now, there is something called, this is something I need to take some time to introduce you to symbolic packages in MATLAB, something called MuPad, which can actually take derivatives and integrals of analytical expressions. I know many of you are using Mathematica, right, in the physical chemistry course. MuPad is part of MATLAB, which functionally is the same as Mathematica. Okay? So next class we'll go into MuPad and ask whether MuPad can integrate that integral for us and see how does it understand the error function, and then build on from that point of view. I think maybe that I will stop there, and I will wind down my paraphernalia here, and then give it to Casey. Okay?
Quick question: how is finding all the area? I mean, the area underneath the curve between two limits any different than finding the cross section of an area?
Cross section of what area?
Cross section area of a curve.
It's the same. You are trying to find out the area under the curve. Yeah.